Right.
Just like I don't believe he took a plane.
Yeah.
That was Jimmy Gusty's dad's plan. That was awesome.
I don't believe it.
Okay, don't believe it then.
Yeah,
He stole a plane.
I didn't. Jimmy Gusty did.
Your name is Sir.
All right. So, worksheet 1.3. How we doing? Yeah.
What do these little like vertical lines mean?
Vertical line. Where are you at?
Like I, T, A, line, B.
Oh. Is that on the right?
Yeah, right here.
Don't worry about those.
Okay, cool.
All right. So, question on number 2. So this will not be quizzed on, but let me just go over it, make sure you're good with it, because you will see it again. This is like number 2, P, A, such that B. Okay? So what this means is this. Let's say I said you're going to draw 2 cards, and you want to know the probability that the second card is a king, such that the first card was already a king. Okay? So this means, what's the probability of this happening, being that this already happened? Okay, and it sounds kind of funny. So let's say we want to know what the probability of drawing 2 kings, or 2 cards, being the second is a king, while the first was already a king. Best way to think about it, I throw you 2 cards, 1, 2. I say, okay, look at the first card. If it's a king, we're going to continue on this adventure. If it's not a king, we're not even going to worry about it. So you just give them both back to me. That's basically what you're doing. So what would the probability of you drawing 2 cards, the second one being a king, being the first was already king? Well, the first being a king is 4 out of 52 times the second being a king. It's going to be 3 out of 51. And then you just multiply that together.
Okay, so how do we do this on the homework?
It says 0.7 and 0.4.
So what does that mean?
Okay, so number 2, probability of event A is equal to 0.7. Probability of B is equal to 0.4. So section B says, find the probability of A such that B. So we want to know the probability of that happening, being this already happened. So it's going to be 0.7 times 0.4. And then the opposite way, this way, is going to be 0.4 times 0.7. You're like, well, that's the same thing. Exactly. In that case. That's all it is. So 0.28.
And then is A, you add them together?
Multiply.
Multiply. And then isn't that all the same thing?
For the most part, yeah. It's a weird example. All right. I want to go to the Venn diagram. Is it number 10? Number 10. So, all right. So 45%, there was a survey given, 45% like hamburgers, 25% like pizza, 55% like chicken, 15% like pizza and chicken, 25% like hamburger and chicken, 5% like all 3, 5% like pizza but not hamburger and chicken. So it's 3 events. That's what you're going to draw. So then you look at it and say, all right, let's make this hamburger. So I'm going to make that 45%. But it's not truly 45% that sits in this outside region. We have to design it from there. Pizza, we have 25%. And then chicken was 55%. Is that okay so far? And then we know that pizza and chicken accounts for 15%. So what does this number drop down to right now? 10. Good. And then this one would drop down to 40 because 15% is there. And then hamburger and chicken is 25%. That drops down to 20. That drops down to 30. Or 25. Or 20 and 30. And then all 3 is 5%. And then we have, they like 5% likes pizza, but not, okay. Right, so then that means this is, so let's start making our thing. So this is only 5% here, and that's because of that. Okay? So then, if we realize that's 5%, I'm not worried about this 25% other than this, and this have to add up. And then this, what is that going to be? The question mark, the intersection between hamburger and pizza. Because you have 5% and 15%, that's 20%. 20% and 5% is 25%. So that's got to be 0%. So of this survey, 0% of the kids liked hamburger and pizza. They might have liked just hamburger, they might have liked just pizza, but they didn't like both of them in that case exclusively. And then we had 5% that liked all 3. What's that? All right, so what is this value going to be here? Shh. What's the hamburger exclusive, folks? 15, because if I add these together, I get 30. 45 minus 30 is 15. So 15% of our population surveyed are exclusive to hamburger only. And then, what is this last portion here? So if I add 15 and 5, that's 20. So I get 45% is the combination. So what does the chicken exclusive have to be? 10%. Okay? So then we get, oops, wrong side. So find the probability a kid likes hamburgers or pizza. Find the probability they like hamburgers or pizza. So what this question is asking is this. What is the probability of a person liking this and this or this? What is it? Add them together. 20%. Okay? So I add the 15% and 5%. Find the probability a kid likes pizza or chicken nugget. Pizza or chicken nuggets, but not hamburgers. Pizza and chicken nuggets, 15%, because 5%, 10%, good. And then find the probability a kid likes all 3. Yeah.
So what about, since it says or, because it could be either or.
Right. That's why I'm adding them together and not multiplying them.
Okay, yeah.
Okay. And then if they like all 3, it's the very center, which is 5% of the population. And then find the probability a kid does not like either. Any ideas? Doesn't like either. Like any of them. Got 1 0%. Do you just add them all up?
Oh, it adds to more.
What are we adding though?
45, 25, and 55.
45, 55, 25. That's going to be bigger than 100% though.
Are we adding 15, 10, and 5?
15, 10, and 5. What if we did that? Let's look at this. Shh. If I added 15, 10, and 5, shh. What else do we have? So that's how much? That's 30. Add this. That's 35. Add this. 45, 55, 60. 75. So 25% of our population, because what I did is I add these up, and then also that, but that's, if you add 0 to it, it's not going to change. Okay, so the other was, we took, God bless you. God bless you. We took a survey, like if we did a survey of this class, and I gave you 3 choices and a neither. And I said, pick up to 3 choices. Okay? So you could be like, oh, I like hamburgers, pizza, and chicken nuggets. So you are part of the 5% category. But then, so being you're part of the 5% category, let's say I come over this row, and he says he likes chicken nuggets. Well, we have to add your chicken nuggets to his, but being that you like all 3, we have to be the exclusive event. So we can't add the 45, 25, and 55. The big indicator why that doesn't work is because it goes above 100%. Okay, so if I add the 15%, which is hamburger exclusive, the 5% pizza exclusive, the 10% chicken exclusive, the 25% that's hamburger and chicken, the 15% that's pizza and chicken, and then the 5% that's all 3, that adds up to 75%. That means 25% of our population put a neither vote. They don't like any of those.
You added up all the exclusive ones.
Add up all the ones. So the important thing on these is make sure that you have found these values. Okay? Because 45% of our population does like the hamburgers, but we have to say, well, we need to less that and that in order to get the true hamburger exclusive people. If we did that, if we counted the 45, the 55, and the 25% and tried to add it up, we are counting the same person multiple times. Yeah. 9?
Yeah, let's do stats. I mean, we should
Do what?
What did you tell me about? He said do
That's why I'm picking them. I know. She's right on. That's double L. She's good. She's not like you. I'm ripping on Parker boy. Don't worry.
Farm fresh eggs.
Farm fresh egg boy over here. All right. Assume that 6. Assume that 6 of 60 tax returns of an auditor's desk contains errors. 6 of 60. The auditor chooses 3 of the tax returns randomly. What is the probability that all 3 of her tax returns contain no errors? Okay, so there's 54 out of 60 times 53 over 59 times 52 out of 58. And I don't know what that comes out to. It's because there's 54 that aren't incorrect. So I'll go 54 out of 60. So I've picked one. And now I'm going to pick another one, so now there's no longer 60 out there, there's 59. And assuming that first one was no errors, that means that 53 of them left don't have any errors. And then I have 2 in my hand, that means there's only 58 left. And that means that if I assume these 2 don't have errors, that means there's only 52. So 54 out of 60 times 53 out of 59 times 52 out of 58.
Why is this different?
What?
Wouldn't it be
Yeah, I'm a visual person.
Right?
Wait, why would it not just be like?
Watch. Do you agree with that so far?
Yeah.
Okay? That means, shh. God bless you. Right? Anyone not agree with that?
Wait, I just.
Okay, go ahead.
Why would it not be 0.9?
is 54 out of 60.9. Wait, I'll tell you. I will tell you that. Assume the auditor chooses 3. Okay, this is why. This is exactly why.
Okay.
It didn't say that I would pick one up, no mistake, put it back down, shuffle them all back together, pick it up again. I'm not replacing them. I'm going 1 and 2 and 3. Are these 3 perfect? Or are these 3 all errors? Or do I have a combination? That's why.
But they're not independent of each other? I don't know.
Well, I am drawing. So let's say I have all of your tests on a desk. They're all shuffled up. They're all face down. I don't know who's. I picked one up. Let's say, and I knew that of our test, 54 out of 60 were great, and then 6 of them were Fs. Let's say there were 60 people in here. Let's just pretend. So if I pick 3 up, 1, 2, and 3, what's probability, probability, probability? I have to drop down each time. So what I'm going to do is this. The chances that I pick up a good test on my very first, watch, ready? This is going to make sense. That's a chance, if I just pick 1 up, that it's good. Now I'm going to hold it. I'm not putting it back down. Now how many are sitting on my desk? 59. And assuming that the one that's in my hand is good, how many good ones are still on my desk then? 53. So now I have 2 in my hand, and I'm assuming they're both good. I don't know yet. I'm just saying, hey, I know that my chance of finding a good one was originally 54 out of 60. Now I'm picking up 1. I'm assuming this is good. Now I'm picking up another one, assuming this is good. Now I'm going to pick up a third one and assume it's good. That means there would have been 52 left out of the 58. And then if you multiply that all together.
Okay.
That make sense?
Yes.
So you're not replacing.
Okay.
That.
But I feel like we've done problems before where we like take 2 cards and they're independent of each other, and we don't have to do that.
That's if you're putting it back.
Sometimes we're putting it back, but sometimes I'm going.
So if it were to be like, what's the chance to take a good one, and then look at it, and then release it back? That would be.
But here's another thing. Let me ask you this. Let's do this. What would the probability that I pick up a good and a bad? If I was only picking up 2 of them. So you think about it. I have 54 good ones out of 60, and then I have how many bad ones out of? Oh, that's 54. Sorry, 54, and that's out of. Now, does it matter if I picked up a good one and then a bad one, or a bad one and a good one? Not necessarily. So those are interchangeable numbers. The 6 and the 54 could go over each way. Just think about when you're multiplying fractions together. It's top to top, bottom to bottom, then reduce. Yeah. Yeah. There was 6 bad ones. 6 out of 60 were bad. That means 54 out of 60 were good. That makes sense? Do what's that? Yeah, this is number 9 right here. That's number 9. And now the other way was just showing. Yeah. Hey, question. Shh. Let's take the same scenario. The reason I'm going to hit this is you will see it on the test. What would the probability be if there was at least one bad one in our original mix? At least one. At least one. So I'm going to take this right here. That means they're all good, right?
Yes.
So if there's at least one, what am I going to do? There you go. 1 minus whatever that answer comes out to. Okay. Can I borrow your calculator real quick? Just because I can't multiply. So, shh. Over 205,320. Okay, so without reducing this fraction. That's the probability that all three of those that I picked up were good. Now, if I wanted to answer this question, what is the probability at least one bad? Okay, so you're going to take the probability that they're all good, and I'm going to go 1 minus whatever that is, which is like nasty.
So like a whole number one?
The whole number 1.
Wait, if you're doing
Would it be easier to like multiply them all together first and then 1 minus
5 over 59, could you do the same thing, or do you have to?
Say that one more time.
If you're like determining at least one bad odd error, can you do 6 over 60 times 59?
I would go 1 minus the good.
Is it the same thing though?
No, because it's the at least one good, or one bad, excuse me.
So you have
It's not the probability that there is one that's bad, it's saying at least one bad. That's the terminology. Like I said, if you're going to pick 3 and only one of them's bad, you're exactly right.
okay, so
But if it says at least, it's going to be 1 minus. So in this case, without doing much, if there was at least one bad, would be 27.5% or 0.275 or some fraction equivalent to that. Okay, will I accept non-reduced fractions? Yes. Will I accept a decimal of what the fraction would be?
Yes.
How many decimal places think would be good to put?
3.
At least 3. Okay, does that sound okay? Can you convert a decimal to a percent? Would I accept that as well? Yeah, if you had 0.175 and you put 17.5%, that's also fine. Okay? We good? Clear desks. I will check this entire assignment off tomorrow, so make sure you have it, okay?
Just this one or the other ones too?
1, 2, and 3. Yeah, I will check 1, 2, and 3 off. Mainly I'm looking for number 3 if you forget 1 and 2 because they're on your desk at home. Whoa. No, just 1 line. No 1 line. Just 1. Well, it won't say at least 2. It won't say at least 1. That means you could have 1 wrong, or 2 wrong, or 3 wrong. Let's not go there. All right. You are allowed to use a calculator. We put your name on it. Just real quick, and then you need to go to nurse. Okay, put your name on this first, and we'll.